In our previous lecture, we learned how to carry out the process of titrating an acid with a base or a base with an acid. After you have completed those steps, we need to then do the math calculations to determine the molarity of the unknown substance. So let's suppose that we have 20.0 milliliters of a 5.0 times 10 to the minus 3 molar sodium hydroxide, and that's required to reach the endpoint of the titration of 10 milliliters of HCl of an unknown concentration. So in our flask to begin with was 10.0 milliliters of HCl, and by the time we have finished the titration, we've discovered that we need 20.0 milliliters of 5.0 times 10 to the minus 3 molar sodium hydroxide to reach the endpoint. Now these titration data can be used to determine the molarity of the acidic solution. So we know the concentration of the sodium hydroxide, but we don't know the concentration of HCl. So the very first thing we need to do is write a balanced neutralization reaction for this titration. So we're going to be reacting hydrochloric acid and sodium hydroxide, and when we put that into an equation, we have the HCl, and then the AQ after it means it's hydrochloric acid. The sodium hydroxide is also dissolved in water, thus the AQ. And this is another one of those where they kind of like two couples trade partners. And so we're going to have the sodium and the chlorine going together to form our salt, and the H and the OH coming together to form our water. And if you look at this equation, it is balanced as is. We don't need to add any coefficients. And in this equation, we can see that for every 1 mole of HCl, I'm going to need 1 mole of sodium hydroxide to neutralize it. After we've written our balanced equation, then we can calculate the number of moles of sodium hydroxide that are in this titration. We know the quantity and the molarity, and from those two pieces of information we can calculate the number of moles. So we were given 20.0 milliliters of 5.0 times 10 to the minus 3 molar sodium hydroxide to reach the endpoint, and we will use the concentration of sodium hydroxide. We're going to write it over 1 liter because that's the meaning of moles per liter is the meaning of molar. And we want to multiply by the concentration, the volume of sodium hydroxide used. First thing we need to notice is that the concentration is in liters, but the volume that we used was in milliliters, so we have to convert liters into milliliters. And so the relationship that we see right there in the very middle, this one right here, is the relationship for between milliliters and liters. 1,000 milliliters equals 1 liter. You'll notice that the liters will cancel out, and I'm in milliliters. Then when I multiply by the 20 milliliters right here, the milliliters will cancel out, and all I should be left with is moles. That comes from right over there. So our answer will, when we do this on a calculator, will be 1.0 times 10 to the minus 4 moles of sodium hydroxide. So the quantity in moles that was used in this titration of sodium hydroxide is 1.0 times 10 to the minus 4 moles. So we found from our balanced equation that for every 1 mole of sodium hydroxide that was needed to neutralize 1 mole of HCl. So from that piece of information and our answer that we just got for the number of moles, we know that the amount of HCl is going to be equal to the moles of sodium hydroxide. They'll have the same answer because they're in a 1-to-1 ratio mole-wise. So for every 1.0 times 10 to the minus 4 moles of sodium hydroxide, I need 1.0 times 10 to the minus 4 moles of HCl. Okay, now we have the number of moles, and to calculate molarity, we just need the volume, which we do know. They gave that in the very beginning of the problem. So we have the concentration given over here on the HCl. We have, and we'll notice that on the top we have the number of moles that we got from right here. We got that answer from right there. And then on the bottom we have the number of milliliters that we used in this titration, which was 10.0 milliliters. But molarity is not moles per milliliter, it's moles per liter. So we're going to have to convert that milliliter back into liter. And that's the purpose of this conversion factor right here, that 1,000 milliliters equals 1 liter. And our milliliters will cancel out. Okay, now let's review what we've just done. Think of it as a series of steps. The first thing that we did is we started with a balanced equation for the neutralization reaction. It was sodium hydroxide and hydrochloric acid in our previous example. And then we balanced the equation. We found out we didn't need to use any coefficients in that particular one. And they were in a 1-to-1 ratio. And we determined that the chemically equivalent amounts of acid and base are in a 1-to-1 ratio mole-wise. Then we, from that information, we were able to determine the moles of acid or base. In our case, it was a base, sodium hydroxide, from the known solution used during the titration. We knew the molarity and we knew the volume so that we could figure out the number of moles of the base that were actually used. Then from that information, knowing that they're in a 1-to-1 ratio, mole-wise, we were able to determine the moles of the unknown solution. In our case, it was the acid that was used during that titration. And then we determined the molarity of the unknown solution. Molarity is moles per liter. We knew the number of moles of the solute of the unknown, and we divided it by the volume of the unknown in milliliters, so we had to convert it into liters, but then we were able to determine the molarity of the unknown solution. So let's do another problem just to see a little variation here. It says in a titration, 27.4 milliliters of a 0.0154 molar barium hydroxide is added to a 20 milliliter sample of HCl solution of unknown concentration until the equivalence point was reached. And then they want to know what is the molarity of the acid solution. That's our unknown. So following our steps, the first thing we are going to have to do is write a balanced equation. So here's our given information, volume and the concentration of the known, and we also know the volume of the unknown. We know 3 out of the 4 things we need to know. So now we need to figure out the molarity of the acid solution. So write a balanced equation and then figure out what the equivalent amounts are going to be. So this is barium hydroxide reacting with HCl. And notice here we've kind of left off the AQs things for the moment. It forms barium chloride. Remember, barium is a +2, so that's the reason why we have to have a Cl2, and then H2O. And then to balance the number of hydrogens on both sides, we're going to have to put a 2 in front of the HCl, as well as a 2 in front of the H2O on the far side. And I believe that makes the equation balanced. And if we look at our balanced equation, it says for every 1 mole of barium hydroxide, I need 2 moles of HCl to neutralize it. So to have equivalent amounts, I need 1 mole of barium hydroxide, and an equivalent amount of acid, HCl, is 2 moles. Then the known basic solution used in milliliters, and the amount of base used, we can figure out the moles. So we have the moles per liter right here at the beginning. That's the molarity of the base. Then we're going to multiply that by the milliliters of the base, but the milliliters and the liters won't cancel out, so we need to convert liters into milliliters so that all the units will cancel out except for moles. So here, and then once we know the moles of barium hydroxide, then we can figure out the moles of the acid from the unknowns solution. And we know that for every 1 mole of barium hydroxide, I need 2 moles of HCl. So that's like your mole ratio that you're familiar from the stoichiometric problem solution guide. We're actually using that concept here so that we can convert moles of barium hydroxide into moles of HCl. And then we are going to take the volume of the unknown and the moles of the solute of the known, and from that we're going to figure out the molarity of the unknown. So amount of solute in unknown solution in moles divided by the volume. They gave it to us in milliliters, and so we have to have a conversion factor on the end of 1,000 milliliters per liter, so that we'll end up with moles per liter, and moles per liter is molarity. So from our balanced equation, we know that for every 1 mole of barium hydroxide, I need 2 moles of HCl. Then, starting with the molarity of barium hydroxide, which was 0.0154 molar, or moles per 1 liter, and we need to convert liters into milliliters so that when we multiply by our milliliters, they will all cancel out. And notice that the conversion factor needs to be upside down so that the liters will cancel out. And then we're going to put the 27.4 milliliters on the top so that the milliliters will also cancel out. So by doing the math on this, I come up with 4.22 times 10 to the minus 4 moles of barium hydroxide. Now we know that for every 1 mole of barium hydroxide, I need 2 moles of HCl. So we're using a conversion factor here on the right as the this is kind of like what we've been using as our mole ratio. So we're taking moles of barium hydroxide and converting it into moles of HCl. So that's just like the middle part of our stoichiometric problem solution guide. Our barium hydroxide here will cancel out with that barium hydroxide, and I'll have my answer come out in moles per liter. And so I'm just going to take this and multiply it by 2, and I have my concentration, I mean not my concentration, my number of moles of HCl. And then finishing that up, we have the moles, and we also were told that it took 20 milliliters of HCl, and this is moles per milliliter, but molarity has to be moles per liter. So again, we have to have this conversion factor here so that our milliliters will cancel out and our moles per liter will be molar. So our concentration of the unknown hydrochloric acid is 4.22 times 10 to the minus 2 molar. Now here is kind of a summary, kind of like a shortcut that you can use in these problems. You just, the A and the B kind of serve like our mole ratio, like the number on the top and the number on the bottom. And if you look in this statement right here, A is the number of OHs that the base produces, the number of OHs. The B is the number of hydronium ions the acid will produce per acid molecule. And then VB is the volume of the base, VA, volume of the acid, MB, the molarity of the base and molarity of the acid. So the VA, VB, MB, and MA are a very common relationship that we use in titrations. This, adding the A in front of it here and the B in front of this one is what helps us if the mole ratio of acids and bases are not 1-to-1, then we need to put in what those numbers are. So like in the previous example, we had 2 hydroxides in barium hydroxide. So the A would have been 2. So this number right here would have been a 2. Not too good at making 2's. And the number of hydronium ions produced in HCl is 1. So this right here is kind of like serving the purpose that what we did in the previous steps as a mole ratio. So this kind of is a shortcut from your the steps that we went through. You can use that if you want. And that takes us to the end of chapter 15.